Hey everybody, today's lab is Lab 4, Oscillations. First thing is to figure out the goal of this lab, and the goal is pretty simple. We're given complex motion and we're supposed to examine and predict it. How are we going to do this? Well, first, we're going to use Tracker to map the motion. Then, we're going to create a model to predict the motion, and finally, we're going to create a graph of energies that are acting in the system. Now, there are some important ideas we have to understand. The first one that we use every time is Newton's second law. That is that the final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. Simply used to find what the new velocity is after a force has acted on an object. The next important idea, a new one, is the energy principle. The idea is that the change in energy is equal to the change in kinetic energy plus the change in potential gravitational energy plus the change in spring potential energy. Now, there are other kinds of energy. We've got thermal, electric. We also have the idea of work. In this particular one, we're just using kinetic, potential gravity, and potential spring. Now, here, we have to be able to find those energies. We have kinetic energy is equal to 1/2 mv squared, m being the mass, v being the velocity. We have potential gravitational energy right here, which is simple, mgh. That means that potential gravitational energy is equal to the mass times the gravitational constant, which is 9.8 meters per second squared, times the height. Finally, potential spring energy, 1/2 ks squared, or 1/2 times the spring constant times s, s being the current length minus the relaxed length. The relaxed length being if you just left the spring alone with no forces acting on it, it would stay at this length. Now we are given a video, and here it is. The video we have to track. As you can see, it's quite complex. They're going all over the place, but with some tracker magic and a couple of givens, pretty easy to do. Here are the givens. We are given that the system that we're analyzing is the mass or the weight, the spring, and the earth. This allows us to use the energy principle and, most importantly, to set the energy principle equal to 0. That means that the change in energy is equal to 0. Next, we're also given that the time of oscillation is 1.524 seconds, and that the length at release is 0.7 meters, and the mass of the weight is 0.402 kilograms. Now, the first thing we need to do from there is find the spring constant. That's pretty easy. We have t, period of oscillation, is equal to 2 pi times the square root of mass divided by the spring constant. A little bit of work down, we get that the spring constant is equal to 4 pi squared times the mass, 0.402, divided by the period of oscillation, 1.524 seconds squared, meaning that K is equal to 6.83 newtons per meter. Now, using that data, we have to find the initial spring length. Now, that's going to be when the force of gravity is equal to the force of the spring, or mg is equal to ks. S, as I said before, is length minus L naught. Trying to find L naught, so now we know that L naught equals L minus mg over k, giving us an L naught of 0.123 meters. Now that we've tracked the data, we have gotten our data from the tracker, and we've talked about how to find everything. This is putting all of that into the model, the prediction model. Right here we have the givens. As you can see, we have the mass of the ball, we have the position. This is the position that was given by the tracker data. We have g, which is the gravitational constant, ks, the spring constant, and L naught. In this part, pretty much just converting the equations we saw in the important ideas section into the model. Here we've got kinetic energy, here we've got potential gravity energy, and here we have potential spring energy. Finally, we have forces. We talked a lot about this. F-grav is a vector in the negative y direction. That's why these two are 0. There's simply mg. This force of the spring is in the negative y direction as well, and that is the spring constant times s times L hat. And finally, net force is equal to F-grav plus F spring. The very final thing is calculating the energy change. Here we have K, the equation we saw before, and delta k. As we all know, the change in something is the final minus the initial. So this is finding the change in k, the change in UG, and the change in US. Finally, what does it mean? Is the energy principle satisfied? Now, as you can see, there's a whole lot of colors here. The important one is this. This yellow line is the change in energy, delta E, which should be equal to 0, and as you can see, it maintains along 0 the whole time. The very final thing we have to do, the final what does it mean, is the XY oscillation period. This is a simple graph. Positions, frames, the top here is X, and the bottom here is Y. Now, we're looking for the X period oscillation. We just do one period like this. It's about 18 frames. This comes out to 17, 18, 17, 18, giving it an average of about 17.5. While on X we look for the lowest point, on Y it starts at the highest point, so we're going to start at the highest point again. And this is about 16, 17, 16, 17, 16, and 17, giving an average of 16.5. Now, assuming 10.5 frames per second, X is once every 17.5 frames, meaning the period of X is 1.667 seconds. Y, on the other hand, once every 16.5 frames, is 1.57 seconds. Thank you very much for watching, and join next week for a free-for-all lab.